Good evening. I know it's Friday and we're all tired. I've been teaching all week, so if you start to not to understand what I'm talking about, please tell me, and then we will try to make it better. So yeah, let me present myself, introduce myself. So I'm
so that people can listen to.
no.
Sorry.
So let me introduce myself. Yes.
Okay.
So
Thanks a lot. Everybody here signed your attendance sheet. Okay. Thanks.
So I'm a geochemist. I'm working not far from here at the Institut de Physique du Globe de Paris. My training is geology, but I'm a geologist that had a bad turn in its life, and I'm going to introduce you to today a concept that has appeared in the scientific literature, let's say 1 decade or 2 decades ago. Which is interesting from a political point of view, and this is what I'm trying to show you today, that this is one of the frontier objects, the kind of frontier object that is interesting to establish the communication between scientists, experimental scientists, natural scientists, and social sciences, and at the society. So I'm going to tell you about this scientific initiative. Where does it come from, and where we think it is going to lead us. So what is... j'ai pas la main. Okay. So if you are interested, I advise you to have a look to this book. It's a really big book. Heavy, and it takes a long time to be read, fully read. It's a book that I've been edited for an exhibition called Critical Zones, which is the title of my talk today, but which was edited by, and so the exhibition was organized by two philosophers. One philosopher, Bruno Latour, and an expert in media, and both unfortunately died a couple of years ago. Bruno Latour and Peter Weibel organized in Germany at Karlsruhe an exhibition called Critical Zone, in which we had this interesting assembly of scientists, social scientists, experiment scientists, artists, philosophers, and many other people on this theme of critical zone. I'm going to go into more details, but just let me read this sentence of Bruno Latour that I like quite a lot. You want to land on Earth. So this idea is that so far we have been globalized, and now more and more we have the need to land somewhere. You want to land on Earth. Why? Because we're hanging in mid-air, headed for a crash. Is it down there? Pretty tense. Is it a war zone? No, it's a close. It's a critical zone, a few kilometers thick, where everything's happened. Is it habitable? Depends on your chosen science. Will I survive down there? Depends on your politics. And I like much this couple of words, because I think they completely summarize what I am going to talk about today. And so this exhibition, you can still find traces of the exhibition on the web. It was in Karlsruhe at the Zentrum für Kunst und Medien in Germany. And so I'm going to tell you more about what is, I do nothing, okay, about what this critical zone concept come from, and where it's, what are the recent developments of that concept. I want to spend time on the way we scientists are trying to get organized to develop this kind of critical zone science, which in a word is a systemic science, an integrated science. And what does it change to the Earth politic? But in the Anthropocene, it is this new epoch of the human and geological history. But I'm not going to be too long on the last point, 1 to 4, by the way, the 3, because it's not my expertise. I have people that I need to admit. Yeah? No, I don't do anything? Okay, thank you. Okay, so the definition of the critical zone is as follows. It was proposed by a US National Council for Research, NCR, in 2001, which is a committee which is trying to organize a big direction of the US, of the research in the US. It's an important committee. And is fixing the objective for the National Science Foundation, which is a big science foundation in the US. It's the skin of the Earth. Basically, it's a zone which is comprised between the sky and the rocks, if you want to make it very short. It's where life and where everything is happening, which is basically the human habitats. And this zone is critical, and I'm going to show you why is it so critical, both for the planet and for the humans, and it's critical for our future on that planet. And what is interesting about this zone is that it's not a new entity. We are not discovering something new, a new ocean on a new continent, right? It's something that exists, but have been so siloed and compartmentalized in the history of science that it has become very difficult to study it as a whole. Okay. So what is important, and this is the reason why I'm here today, is that this zone, which is a critical zone of the planet, is the habitable zone of the planet. And if you think a little bit of that, we're not living on the globe. We're not living on this image which was taken from the space in the 1970s, the blue marble, so to say. We're living on a very, very thin pellicule at the surface of the planet, where everything is happening. And so this is a graph. I'm not proud of this graph, and I have a series of diagrams from which I'm not proud, but this is the best I can offer. And we're working. I'm not sure I'm going to have time today to go into those directions, but we're working on improving our representation of the system we live in, because actually I do think that we still don't know really the planet on which we're living. So this is a bad diagram which is showing you the different reservoirs, compartments, which are concerned by critical zone science. And basically critical zone science is to say, well, all these objects have been studied by different sciences, are monitored by different institutions, for example, in the States, in France in particular, but there is no longer the way we should be organized. And we should look at that think, as one of my colleagues in Berkeley used to say, this think as a whole. So what is this think? It's comprising the lower atmosphere, the arable soil. The notion of soil is very difficult to handle. Maybe you already meet this difficulty that the soil means everything and nothing. And everything is talking about the soil without knowing exactly what he's talking or she's talking about. In particular in France and in Europe, we have this new law, which is the impermeabilization, zero impermeabilization law, that talks about the soil in terms of square meter or square kilometer. And from a geochemist or a geologist like me, the soil is everything but a square kilometer, or it's something which has a volume, which has a life, which has a dynamic, and it's not a surface, right? Beneath the arable soil, you have the geological soil, which I'm interested in. I'm going to show you how it has been formed on the planet with time. But you also have in this critical zone the water, okay, which is not separated, which is not to be separated from the soil. The pore water that you don't see, the groundwater from which we take most of our water resource, in particular here in Paris, the running water, which is, as you saw, for example, 2 weeks ago in Spain, can be really dangerous when extreme events occur. What else? In the critical zone, you also have the rocks, because as I'm going to show you, the rocks are part of the system, because the rocks being transformed by a series of processes are providing the nutrients to life. Okay, so basically you cannot do ecology without taking into account the rocks. Keep that in mind, that the phosphorus that you need every day, because it's a component of your teeth, of your bones, of your DNA, is coming from the rocks, okay, by a series of transformation that I'm going to describe in a minute. But also in the critical zone, we have the ecosystem in a reduced sense, that narrow sense. I would say, that is today used. Ecosystem is the green stuff at the surface, a list of species that we need to protect on the planet, but also a world, a deep biosphere, which is pretty unknown, basically, and which is doing, I would say, most of the job. And there is a lot of research going on that deep biosphere, which is beneath our feet and which is still very, very badly known. So this is a bad diagram, and this is another bad diagram, which is showing that the critical zone is not a vertical concept, okay? It's also an horizontal concept, because when you live, for example, here in the Mississippi Delta, you depends on what happened in the mountains upstream, okay? You depends upon the status of the glaciers. If you, one of the best example is the Californian interior plain, where most of the fruits from the US are grown. If you don't have water falling on the Sierra Nevada, you don't have water into the Californian deep aquifer, the Californian plains, interior plains, okay? So everything is connected, not only vertically, but also horizontally. And so in that bad representation, I'm trying to show how you are connected, or we are connected, to basically the global water cycle, and I'm going to stop a little bit on that notion of global water cycle. And I will come back on that later, but just to say that the problem of the critical zone as a whole, as a thing, is that it has been studied, and it is studied by disciplines which are very, very different, which are not even able to communicate, because they're talking about the same object, but with different languages, names, words, okay? And it's like a game here. I've put on that diagram, bad diagram, all the disciplines which are can be how to say, concerned by the study of this critical zone, the livable part of our planet. So it ranges from ecology to, of course, meteorology, climatology, hydrology, biogeochemistry, geology, geomorphology, etc., etc. But today, you can have a master in hydrogeology without being a hydrologist officially. And it's even worse when you look at the institutional state. For example, in France, which is probably not the best country, but on that regard, but in France, we have an institution which is monitoring the rivers, INRAE, and we have another institution which is monitoring the groundwaters, okay, the aquifers. From a geological point of view, it's nonsense, because both are completely connected. So it should be the same institution which is looking at the groundwater and the institution which is looking at the running water, because both are connected in a way or another. This is a kind of completely weird things that we have now, after 2 centuries of science divergence and specialization. So where are we living? We're living on a zone which, from an energetic point of view, I have a training in physics. I'm not going to bother you with too much of physics, but a couple of numbers are not bad to remind. So the critical zone, the surface of the planet, the part we live on the planet, is fueled, so to say, by 2 sources of energy. The first one is the one we think of very easily, which is the sun. Okay, and this is probably what you've learned, that everything at the surface of this planet, the habitability of the planet, is due to the sun energy, which is fueling the surface of the planet. And that's true. It's 180,000 terawatts. So a watt is a joule per second in terms of energy unit. It's a huge amount of energy, but it's coming from what I'm calling Helios here, the sun. Helios being the Greek god of the sun. It's a lot, but actually it's not concerning a big depth at the surface of the planet. If you are, for example, an earthworm, you're not really interested by this Helios energy, because you are deeply buried into below the surface, and the sun energy is not directly concerning you. There is another source of energy which is absolutely not known, except in some regions of the world where geothermal energy is starting to be important, which is the energy from the deep Earth. Okay, and I have a couple of slides I want to show you, because it's important to remind that the planet, the Earth is a planet which is warm. And why is it warm? It's warm because it's radioactive. Okay, it's full of radioactivity inside, and these radioactive reactions are producing a lot of heat. And the way the planet is dissipating this heat is as a special way that gives birth to the reliefs. Okay, and a planet that would be flat would be an non-habitable planet. Okay, so let me go into these details in a couple of slides, but just remind that the planet is habitable. The planet's habitability is due to the, how to say, this meeting between two sources of energy, the energy coming from above, Helios, and the energy coming from below, which I'm calling Hades. Okay, let's talk a little bit about Hades, the energy from below. So this is a couple of figures that you may or may have already seen, or maybe not. And if not, this is not normal, because this is important information that everyone should know. So the planet is hot. It's a radioactive planet. The deep interior of the Earth is containing radioactive elements which are producing a lot of heat. This is the way humans are, at least in France, are producing most of their energy. And the manifestation of this, the dissipation of the heat of the planet is plate tectonic. Maybe you've heard about plate tectonic. This is one of the biggest discoveries in science during the last century. The plate tectonic is a theory. It's not a theory, it's a model that says that the surface of the planet is divided into rigid plates, and these plates can be separated, or the reverse, can collide in certain parts of the world. And when two plates collide, you got a mountain range, okay? Or you got volcanism. And this is important for the planet, because the relief, which is originating from the motion of plates, is what drives the water cycle at the surface, okay? Again, if the planet would be flat, there would have been no life possible on the planet, okay? So relief, and then plate tectonic, which is the expression of the cooling, the secular cooling of the deep Earth interior, is fundamental for the habitability of the Earth. The second source of energy, and I don't have to convince you that it's an important one, is the sun energy. And just look at this absolutely wonderful map, which is based on satellite data, which is giving you the mean annual temperature at the surface. And you know that the intertropical zone is warmed up by the sun energy, and the latitude, the northern or the southern latitude, have a sun energy deficit, and this is resulting in difference in the mean annual temperature, ranging from 25 in the tropics to minus 50 eventually in the Antarctic. This is mean annual temperature. Again, it varies, of course, with time. So big energy difference which are causing, so the fact that the ocean is warm is a source of the ocean evaporation. And this is a map. This is another beautiful map that which is has been possibly assembled based on satellite data, which is the amount of oceanic water which is being evaporated by the sun energy. And you do see that it's in centimeter per year. And you do see that the places in the world where the ocean is being evaporated is exactly the part of the planet where the sun energy is maximum. Okay, so the first consequence of the warming of the sun, the influence of the sun energy, is to create the evaporation of the ocean. The second, and then you got this water cycle, which you probably have known already at the surface of the planet, which is a characteristic of the planet. There is no other planet in the solar system, in particular the rocky planets which are surrounding the Earth, which are the Moon, Venus, Mars, Mercury, have no water cycle. The Earth is the only planet amongst this rocky planet which has a Earth's water cycle. Okay, again, fueled by two sources of energy. I insist on that because I think this is really important to say that if there is a water cycle on the planet, of course there is water. This is the first ingredient, but this is also because you have this sun energy and the deep energy which is creating the relief. And without any relief, again, there would not be any water cycle on the planet. So you have here the basic numbers of the global water cycle. It's interesting to stop 1 minute on those numbers. So most of the evaporation of the ocean occurs in the tropics, as I said, and we know the global flux, more or less. It's 434,000 cubic kilometer per year. It's a huge amount of water, which is basically precipitated in the form of rain on the tropical oceans. Okay, so everything could stop there. I mean, the water cycle on the planet is just evaporation in the tropics, precipitation on the ocean in the tropics, and that's it. But this is not the interesting part of the cycle, and life is not relying on that cycle. A little bit of the vapor, which is in the atmosphere, which has been created by the evaporation of the ocean, is leaving the ocean, and it's going to the northern latitude or to the southern latitude, and that's a good thing because it's precipitating onto the terrestrial surfaces, okay, onto the continents, which are the emerged part of the terrestrial crust. But look, on the continents, on the terrestrial surfaces, it's 107,000 cubic kilometer per year, which are precipitated. This is much more than the difference between 434 and 398 here. So we have a problem, which is that the amount of water which hasn't been precipitated on the ocean in the tropical region is not the amount of water which is precipitated on the continents. There is an additional flux. If you need to meet this 107,000 cubic kilometer per year, you need a new flux of water vapor to the atmosphere. And we know this flux quite well. It's coming from, it's called evapotranspiration. And I'm sorry, on my slide, each time I say I will correct the slide, but I never correct the slide. It's not evaporation, it's evapotranspiration, meaning that most of the job is done by forest and vegetation, basically. Okay, you need to see a tree as a water pump, actually. The tree is using water, but a little, very, very little amount is used for the internal metabolism. Most of the water that a tree is taking up in the soil is transpirated to the atmosphere. And at the global scale, it's a huge amount of water which is annually being transferred from the surface to the atmosphere. Look, it's 71. And if you add 71 to the difference between the evaporation and the precipitation, you get this 107 that I was talking about before. And so it's important to say that because when we talk about, I'm not going to talk about that today, although I like this idea of Gaia as a living planet, the fact that the living organisms are making everything possible to maintain, to sustain their own living conditions. And this is one of the Gaia arguments, that the water cycle is what it is because of living organisms. Okay? And you can even go a little bit farther. You can even say that there is an ocean of the planet because they are living organisms, and the living organisms are keeping the ocean in its present state. Okay, and there is another interesting characteristic of the planet, which is photosynthesis. Photosynthesis, you may know that probably, and I think you have lectures on that earlier, is the kind of a miracle reaction, which is the fact that some of the living organisms, not all, not us, for example, unfortunately, are able to use the solar energy and to make their own organic matter. They're doing organic matter according to this chemical reaction. I'm sorry, it's one of the only chemical reactions today. CH2O is what you are made of, organic matter, living organic matter. And some of the living organisms on the planet, the green organisms, especially, are able to use the atmospheric CO2 combined with water to make up this organic matter. There is a waste, which is oxygen. It's a waste of that reaction, but of course it's not a waste for us, because the animals, which are doing exactly the reverse reaction, are consuming the oxygen back and then are reintroducing the CO2 in the atmosphere. This is what old chemists from the 19th century, for example, the famous chemist, the French chemist, which was beheaded at the French Revolution, Lavoisier, already at that time wrote 9 pages saying that photosynthesis and respiration were responsible of a vital, and I like the term vital, cycle, which was maintaining the habitability of the Earth. He was wrong, because he didn't know a process that I'm going to talk about in a minute, which is actually the true process which is responsible for the Earth's habitability, but the idea that there is an equilibrium between photosynthesis, which is a forward reaction, and respiration, which is a backward reaction, is essentially correct. Okay, so basically what living organisms do is putting some solar energy in reserve. They're constituting a reserve. They're creating chemical energy from solar energy, and all the living organism chain is relying on that. Okay, you can interrupt me if you have questions, or if it's too complicated, we can take the time necessary to go into more details. That's okay? Yeah? So, the big question, and as I am a geologist, this is a big question I have always asked myself: why is a planet so particular? Okay, why is there life on our planet, and why Mars has no life, no water cycle? It had a water cycle. We know that quite well, but this water cycle just shut down at some point in the history of the planet, Mars. But on the planet Earth, everything has been maintained. Okay, but the Moon doesn't have any water cycle. Venus doesn't have a water cycle, and Venus is not habitable. So why is planet Earth so particular? And the answer is that this water cycle that I've introduced to you earlier is causing some transformation of the rocks which are below. So the Earth, which used to be at the beginning at least a rocky planet like Mars is, or the Moon is no longer a rocky, a hard rock planet on which nothing can be cultivated, in which life cannot develop. It's something which is covered by a soft pellicule, okay, which is not something which was brought from outside. It's something which is created by the transformation of the planet itself, okay? And this is what I'm working on, actually. I'm a geochemist, as I said, and I've been working in my career on that transformation, which is specific to the Earth, that we call chemical weathering, okay? It's not a very sexy term. It's coming in English from weathering. You see the origin of the word, weather, okay? The rain is transforming the rocks. But actually, my point today is to show you that it's not the rain which is transforming the rock. This is another agent. And I'm going to introduce you to this new agent in a minute. In French, if you're interested, we don't say chemical weathering. We say altération chimique, chemical alteration, which is a word that exists also in English, but which is nicer, because when you alterate something, you transform it in situ, so to say, okay? And so for that particular case, the French word is better than the English denomination, okay? Alteration, you used to be a rock, you getting altered and you giving something else, okay? Alteration. And just let me show you pictures, because as a geologist, I spend a lot of time in the field, sampling stuff and taking it back to my lab to analyze it. And so this is a quarry. This is one of the places I like the most. It's in the Caribbean. It's in the island of Guadeloupe in the Western Indies, for those who know the place. And this is a picture on which you see the different components of the critical zone I've introduced you earlier. You do see the atmosphere, not the whole atmosphere, the atmosphere, local atmosphere, okay, the one that those trees here are using to live, okay? You do see the forest, which is a dry tropical forest in that case. You see a very thin arable soil, which is here. I don't know if you see my pointer. Yeah, arable soil, which is very thin, because in the tropics, the humus, the part of the organic part of the soil is very reduced, just because there is a lot of bacterial activity, and when a leaf falls on the floor, its life expectancy is like 1 week. It's disappearing quite rapidly because there's a lot of fungi and bacteria which are remineralizing it. Below, you got some white stuff here, which is what the geologists call the saprolite. Sapro, it comes from a Greek name that means soft. So this is like a rock. It has the structure of a rock, but it's not a rock, it's soft. When you take your hammer and you try to hammer it, it's completely soft. And basically, it's made of a mineral that you know, because it's a mineral which is pretty well known, which is a clay mineral, okay? It's kaolinite. So maybe you've heard about kaolinite before, or kaolin, because this is a material which is used to make ceramics, in particular porcelain in the history. So this material is particular, very particular. There's water, which is not visible on this slide, but there's water which is circulating. This is a place where it's raining quite a lot. It's raining 3 meters a year. It's raining every day, and the water is infiltrating through this layer of soil here. And there's something you don't see on the slide, which is 60 meters below is a bedrock, what we call in geology the bedrock, okay? The non-weathered rocks, the non-altered rock, the true ones, okay? The one for the reason of this quarry, because people are mining the rocks at that place, and it was very interesting. The first time I went to this quarry, the guy told me, the guy which was leading the quarry told me, oh, you're interested by this white stuff at the surface? Okay, this is the one we want to get rid of because we want to exploit the rocks. We're not interested by the weathered pellicule, okay? And because we were coming with geophysical instruments, trying to make an echography of the quarry, he was quite happy to see us because we were able to tell him how deep was this unfertile layer for him, but which is the habitable part of the planet, okay? So I'm smiling, but it's not something we should smile of course. And in that quarry, I didn't take it with me today, but I could have taken with me today. I isolated this rock that I cut into 2 parts. It's a rock which, to me, is a, how to say, an earth, or in a reduced size, so to say. So when you look at the interior of that rock, which is a former, an ancient volcanic bomb, it's something which has been emitted by a volcano. Guadeloupe Island is a former volcano. So imagine a volcanic bomb, which is lava, which is going through the air and is cooling down and is coming back on the ground, where it stayed for like 1,000 years. And at the interior of the bomb, you do see a gray rock, which you don't have it in hands, but it's really hard. It's hard rock. It's a hard rock. It's my bedrock, okay? It's an andesite, for those of you which are interested by naming the rocks. It's a volcanic rocks. But what is interesting here is that outside of the rock, you have a sphere which is completely altered, transformed, okay? And this is an example of what chemical weathering is, okay? So the yellow pellicule, the yellow stuff, which is made of clay minerals and iron oxide, and the iron oxide basically rust, which is giving the color, okay, of that yellowish pellicule here, is coming from the transformation of the rock, which is below. okay? Which is not something which is, I think, evident when you just look at the rock, okay? But if you do a chemical analysis and a number of studies, you can show that, yes, the yellow stuff around the rock comes from the transformation, the weathering, okay, of that volcanic rock, okay? The first time I met Bruno Latour, the philosopher, I showed him this rock. What are you doing? I'm working on that. Okay, so you're the Freud, Sigmund Freud of geology. You're interested by the degradation of rocks, you know? You're not interested by the perfect, ideal cases, bedrocks. You're interested by the way these rocks are being, you know, altered, transformed. Okay, and I think it is completely right. But what is important for our purpose today is to understand that because of this chemical transformation, the planet has become habitable. Okay, and the rover, maybe you've been interested by this rover that circulated at the surface of Mars a couple of years ago, the Eternity probe, and a lot of billions have been spent to make this rover moving on Mars. This rover didn't discover clay minerals, okay? So clay minerals are really the smoking gun of those transformations that are existing on the planet Earth that doesn't exist elsewhere, okay? And so I don't want to bother you with chemical reactions here, but just one reaction here, which is showing that if you want to transform a rock into a clay, you need an agent which is not water, but which is what the chemist called a proton, H+, acidity. And where does this acidity come from? It comes from the dissolution of the CO2 in the water, which is infiltrating. So the agent which is transforming the rocks at the surface of our planet is not water. Water is important. It's contributing to the process, but it's not the main agent. The main agent is CO2 from the atmosphere, or the CO2 which is being produced at the surface of the soil by the decomposition of vegetation. Okay? So it's interesting. And in my metaphor of Helios and Hades, the transformation of the rocky planet on which we are living is due to the action of the atmospheric CO2, which is an acid, to the rock, okay? And it has been discovered by a guy a long time ago. This discovery was completely forgotten. He was a French mining engineer. His name is Ebelman, and I think this guy should be better known. His name is on the Eiffel Tower, not for this kind of discovery, this kind of discoveries he did, but he was the first that enunciated in the middle of the 18th century that in order to form a clay mineral, you need to have the reaction between CO2 from the atmosphere and the rocks, okay? The reason why he discovered this was that he was a director of the Manufacture de Sèvres, which is a big plant at that time making ceramics. And at that time we didn't know plastic, and so ceramic was a master material which was used in everyday's life. And this guy was trying to understand the way kaolin was formed. At that time, kaolin was not existing in Europe and was bought to the Chinese. And the reason why it was important to understand how kaolin is formed is important, led this guy to discover that the habitable part of the planet is due to the fact that the atmospheric CO2 is reacting with the rocks, okay? So this yellowish pellicule around the rock is a reaction zone between the CO2 from the atmosphere or the soil with the rock, okay? And this is why our planet has become habitable. And as I said earlier, there is a deep biosphere, which is completely unknown, and that's probably is doing the job. This is not directly CO2 which is reacting with the rock minerals, but this is probably at the interface or by the action of living organisms, and that we essentially don't know. And so when we talk about biodiversity, we're talking about the biodiversity of visible ecosystems, okay? But we're not talking about the biodiversity of the bugs which are beneath our feet in the critical zone. You know what? Just because we don't know them. Okay, and each month a paper comes out that discover new species deeply buried under our feet at the interface between the rock and this soft material which I'm naming the critical zone. Okay, so there is a huge amount of work which is being done in the laboratories right now to characterize these organisms. And it's, again, another mention to the Gaia theory, because the Gaia theory was proposed by two persons. You may know that. James Lovelock, he was a biogeochemist. I don't know exactly what it was, but it was geochemist, some kind of chemist. He was working for industrial companies, which are not very, by the way, good companies. And then he was also working with a woman which is very famous, which is Lynn Margulis. And Lynn Margulis was a microbiologist. And Lynn's statement was that everything on that planet is, the habitability, long-term habitability of the planet is due to invisible organisms that we ignore, just ignore, that we don't know, but which are living beneath our feet. Okay, and so this is again an interesting statement that most of the job is done by unknown organisms. And this figure, I like it a lot. It's you see on that figure, it's a microscope image taken under a microscope, and each of these thing here is a bacteria, but you do see that these bacteria are linked together by some kind of tires, and these tires are organic matter. And it has been demonstrated that this is actually conducting electricity. These tires are conducting electricity. And this is one of my geophysicist colleagues that gave me that picture, because he's working on electricity. So he's injecting electricity into the soil, and he's looking at the way the electricity is transferred into the soil. It's a strange job, but you know, he's free to do that. And the way he can interpret his results is impossible if it doesn't take into account special way of electricity to be transferred. Okay, and he's proposing, and I think he's quite right, that it's due to these organic tires which are conducting electricity and which are transmitting the signal, so to say. I don't know if you saw that movie a couple of years ago, Avatar. It's exactly the Avatar story, that everything on the planet is communicating. We don't see it because we don't understand the processes so far, but probably there is something like that in this discovery. And so we are, because the critical zone is basically unknown, we're not going to drill in every village, in every field, etc. We are developing non-invasive methods. Like here, it's a geophysical method. So this guy here are not destroying the ecosystem. They are eating the floor with a big hammer. And doing that, they're generating waves. And the propagation of the waves at the surface of the soil is giving back to us an image of the different material which has been crossed by the waves. Okay, so it's exactly what you do when you go to the doctor and you make an echography. Okay, he's not eating you, I hope so, but the doctor is putting you some acoustic waves on your body, and then he's trying to understand the way these waves are transmitted, and it gives him an image of your body, interior body. And this is the same here. And you do see on these images in green, true rocks, and red, true rocks, and in green and blue, soft material. And you get also an indication of the water content, but I'm not going into the details here. And this is a small stream in the Vosges mountains in the eastern part of France. It's a critical zone observatory. I'm going to show you that later. And you do see that it's incredible the way the lower limit of the critical zone is very dissected, nothing regular. Okay, and so we just discovering a new world on which we are inhabiting. Okay, and again, when you think about this zero artificialization law, no, this is not the way to think in terms of surface. A surface of soil here just near the river has nothing to do with a surface of soil at the top of a hill, you know. And so this is a kind of information that should be taken into account for legal regulation. Okay, so the critical zone is like a conveyor belt, okay? It's formed by the reactions I have been talking about, and it's also deformed or destructed, because imagine a planet on which you only have the transformation of rock, and that this transformation has lasted for billion years. The planet has 4.5 billion years. Then imagine the surface of the planet would be completely blanketed by a huge amount of clays and oxide, blah, 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 and nothing would be fertile anymore. So there is a process, and we know this process, which is completely rejuvenating this critical zone. So it's like a conveyor belt. The thin pellicule on which we live at the planet is constantly created and constantly degraded by processes that we call physical erosion. And you saw these terrible images from Spain last or 2 weeks ago. You had a brutal event of erosion, and the color of the river that crossed the city of Valencia was due to the fact that clay minerals from the soils of the region above the city were rapidly transported to the ocean by these terrible storms. Okay, and this is the way the critical zone is being destructed on the long term. This is a river. This is another observatory. This is the image of a river which is brown, and it's brown because it's transporting material which is being transported to the ocean, which has been created by this chemical weathering reaction that I've been talking about. On the long term, you imagine that this conveyor belt is destructing the reliefs, and that if you can pass, it would take millions of years, but you can pass from that state of a landscape, mountainous landscape, to that step of a landscape that the geologists called a shield or a peneplain, which is almost flat. There's no really flat areas on the planet, but this is in Australia. Or you can think about the Amazonian forest or the forest in the center of Africa. This is the region which are the flattest areas on the planet, and which are dead from a geological point of view, because there my conveyor belt has more or less stopped. Okay, creation reactions are slow, destruction reactions are slow, nothing really happens. And the drama of cutting the Amazonian forest or Congolese forest is that this forest will never be able to come back, because the soil is very depleted. Okay, it has been weathered for so many million years that the vegetation is just recycling all the time its nutrients. And so if you cut the forest and log the trees, then the nutrient stock disappear forever. And the forest, a tropical forest on a flat region that is cut cannot come back. Okay, and this is one of the ecological, very extremely bad situation that we're facing today. Okay, so the good situation, so to say, is a situation where there is slopes. Okay, because the slopes again are providing, and there is plate tectonic, because plate tectonic, the relief, is constantly bringing new material to the critical zone. Okay, and so again, remember of your phosphorus. Okay, when you will eat tonight, think about the phosphorus you're going to ingest. Okay, this phosphorus comes from the rocks, and the only way this phosphorus which used to be in a rock is available to you is chemical weathering reactions. Okay, and if by chance this chemical weathering reaction would stop on the planet, then the planet would die. Okay, and this also explains this conveyor belt, this very famous paradox, so to say, that if you compare two planets of the solar system, this is the Mercury planet and this is the Earth. I think you recognized it. You do see on the surface of Mercury traces of impacts. Okay, the planet has been completely impacted by the many meteorites and asteroids that felt on it. You don't see that on the Earth. And why you don't see the trace of these former impacts that happened, okay? There is no reason why they happened on Mercury, on the Moon, on Mars. There is no reason that they didn't happen on the Earth, okay? But the Earth has constantly rejuvenated, smoothed the surface of this planet, cleaned up the surface of this continent so that you cannot see the trace of these former extraterrestrial events. Okay, so the planet is constantly rejuvenating, and I like to cite then one of my heroes is the father of geology. He needs to be better known. Is James Hutton. He was a Scottish farmer. He's a farmer. The father of geology is a farmer. Okay, yeah, this is important to mention. And he quoted this, we find no vestige of a beginning, no prospect for an end. He was talking about the Earth history. Because the planet is always rejuvenating, cleaning up its thin pellicule, habitable pellicule, you don't know how it started. You have no trace of the beginning. It's like when you enter on a conveyor belt, you're spending a given amount of time, but you don't know when the conveyor belt started. You know, you just took it. And so, by consequence, we have no prospect for an end. So this is more of a philosophical thought. And he wrote a nice book, a terrible book, I should say, because it's almost non-readable, but Theory of the Earth in 1795. Okay, and he, as a farmer, he was questioned, so to say, by the fertility of its soils. Okay, and he understood that agriculture is by nature non-sustainable, because when you do agriculture, you plant something and then you export it, and then you export the nutrients. And see, if you don't have a mechanism which is providing the nutrients again that you have exported, then you lost. It's not a sustainable system. And so he got interested by the way the planet was functioning, so to say, to maintain its habitability over. He didn't know at that time. He didn't know that the planet was billion years old, but at least he was suspecting a couple of tens thousands years. Okay, so the critical zone is critical for the geologist, and this is why this US committee in the advising committee put it on the front of the priorities of the NSF. It's important for climate regulation. It's important for water quality issues, because if you understood me correctly, the water quality is also due to these race-ring reactions which are occurring at the surface of the Earth, which are transforming the planet. It's important for ecosystems because it's the only ultimate source of nutrients, and it's also important for landscape evolution. It turns out that amongst the people the most interested by this critical zone approach are the architects, and I will show you some evidences on that later. Okay, I'm passing on that. Oops. So, why is it so important from a scientific point of view? And then I will move to the question of observatories, and when I will end up with the question of why is it important for new politics. So what is complex in the understanding of the critical zone is that it's really how to say a messy object. It's filled of water, clay, living organisms, gases with different circulation paths. It's complicated to model, okay? And from a physicist point of view, it's horrible. You know, it's something you cannot do because it's too complicated, okay? And so you have a first possibility, which is what people did for decades: go to your lab, simplify the system, and take, like, for example, one mineral. You try to understand how fast this mineral dissolves in the clean conditions of your laboratory. But this didn't lead to any big discovery, because nature is not a laboratory. And so the idea that Pasteur in his time had, which was, oh, I don't understand what is causing the diseases, I'm going to simplify and I'm going to isolate the agent of disease in a lab, doesn't work for that particular study of the critical zone, because we need to deal with a system which is by nature complex. okay? It's a problem, I don't have to go into the details here, but it's a problem of kinetics, meaning the fact that in the critical zone, you have different time scales which are embedded, okay? A bacteria is going to reproduce very fast, okay? Every second, eventually. But the chemical weathering reactions I've been talking about are very slow. It takes, for example, the volcanic bomb that I've showed you before, it takes 100,000 years to do that, to do this couple of centimeters, okay? So very slow reaction. So you should be thinking that, okay, he's talking about something which is so slow that it's completely irrelevant, okay? No, it's not irrelevant because it's a source of our nutrients again. So if we want to try to understand in a more holistic way how this critical zone system works, from a mathematical or numerical point of view, that's really difficult, okay? It's as difficult as, you know, running an economical model, so to say. Large heterogeneities are characterizing the critical zone because if you understood me correctly, the critical zone is not only a matter of climate or local climate, it's also a matter of topography. The type of rock is going to be very important. Land use, which is a human occupation of the land, is very important. So there's a geodiversity. This term geodiversity is not very widely used, or when it's used in a sense which is not, I think, the good one. But by geodiversity, we should think about this diversity of local context that we have when we mix the climate, the vegetation, the geology, and the human occupation. And as I told you already, one of the difficulties of doing critical zone science is that historical fragmentation of disciplines in the history of science. Okay, I've showed you that already. And so the critical zone science can be summarized by what we call our Higgs boson, so to say. And this is a sarcastic view that the physicists have tried to raise billions of dollars to do things which are not really interesting. Okay, like accelerating particles under the French-Swiss boundary. Is it something which is important? Do you think it's important? It's producing a lot of CO2 in the atmosphere. You know that? It's one of the most horrible things in terms of scientific research and environmental impact. Do you think that's going to change our lives? You have the right to say yes, huh? But I don't see any hand raised. Okay, billions. But simply the way they did that was that they had one question. Okay, and they went to see their founders and said, okay, we have one big question we want to solve. And the question was, what is the elementary particle, okay? Under which we can unify everything. And this idea of unification is something which is easy to sell. But when you work on the critical zone, which is the habitable part of the planet, I can tell you that because these disciplines are, divided, fighting with each other, it's really difficult to get a Higgs boson statement. And this is my Higgs boson. Are we able to understand and model the behavior and the trajectory with time of the critical zone, which is the human habitat, in response to the changes which are characterizing the Anthropocene? What do we know about the feedbacks, the regulatory loops that characterize the compartments that compose it? And the answer to this question is that we don't know. Okay? And I want to be very clear about that. If you ask me what is going to be Paris or Toulouse or New York in 1 or 2 centuries, the answer to this question is simply I don't know. Okay, you can say something about the mean annual temperature. Okay, yes, the mean annual temperature of Paris is going to be that of, I don't know, Madrid or Rome. Okay, but it's an information which is interesting, but it says nothing about the way to live in Paris. It says nothing about the way precipitation are going to be in the year. It says nothing about the water resource. It says nothing about the soil occupation, the type of agriculture we'll be able to do in the surrounding, okay? So this is really a critical zone problem, This is an integrated problem, And there is a website which is giving you you put your village on the website, and then it's giving you the village, the equivalent village in 2 centuries. Like you type, I don't know, Rennes, and then you got like a city in Greece, which will have the same mean annual temperature. This is ridiculous, okay? Because no, Toulouse is never get to be, I don't know, Marrakesh, okay? Because the local conditions are not the same. The rocks are not the same. The soils are not the same. The vegetation is not the same. And the people are not the same. And so the people will decide that they want to do at that place. Okay? So how do we, am I doing with the time? Yeah, I'm going to go fast. So how do we scientists, we try to get organized to develop a critical zone science? And this is difficult, okay? And so what we chose to do, and this is why it was interesting for philosophers and social sciences from which we start to be connected, is that we decided to go on situated places, okay? We decided to instrument sites, okay? So really localized. Critical zone science is not a global science, okay? You can do a global model of atmosphere, of the atmosphere. You cannot do a global model of the habitable Earth. It's too diverse. There is too much heterogeneity. It's not homogeneous, okay? And so we decided to focus on zones, places that we call critical zone observatories, on which we try to reconnect all the disciplines, okay? And when I talk about disciplines, I talk about these disciplines that I've put on my ugly diagram before, but this is also social sciences eventually. And what is starting to happen right now, and this is a kind of a miracle that I think in my career I will see the developments, is that social sciences are getting interested by what the scientists or experiment scientists do at a given place. Okay? In that place, what do we do? So we mix disciplines. So it could be, for example, a watershed, okay? A drainage catchment. It can be of different sizes, okay? And what is also interesting for the social sciences is that you can say that a watershed is a bioregion, okay? So it's mentioned to this bioregionalism concept that's developed in the US a long time ago. What we try to do at these places where we meet, disciplinarity meet, is monitoring over long time scale. Because this is something I didn't go into the details today, but this critical zone is characterized by different time scales, and not only very short time scales, okay? The chemical weathering reactions I've been talking about are slow. And if you don't monitor your system for long periods of time, you are not going to understand what happens at a long time scale, okay? Of course, this is very difficult to found an observatory for like 50 years. There's no single funding agency which is going to believe you. Okay, I need money for the next 50 years. Okay, come on. I have money for the next 3 years, and then you'll come back and we'll discuss again. Okay, and this is the way it is, except in France and in China, where we have a lot of money, or not a lot, but we have money, possibly, to conduct monitoring at some sites. And some of the sites, which are part of the network I'm going to talk about in a minute, some of them have been funded for 60 years, which is not bad. Huh? In the former USSR, but unfortunately the end of the USSR stopped the process of monitoring. Some sites were monitored for 50 years, and when you have a cumulative information of 50 years, believe me, you understand a lot of things that you're not able to understand when you have just 3 years of observation. What is interesting about these critical zone observatories is that they are anchored to an initial overarching local and societal question. I'm going to show you an example. So the idea is to use nature as a laboratory, okay? Because it's complex, I'm not going to go in a lab, in the clean lab. I'm going to use nature as a lab, and eventually I'm trying to choose the places to vary, for example, climate or rock type or land use or some kind of other parameters that I think are playing a big role in the system. Okay. So the first network, this is what the first network was founded in the US. You can see, you can have information on those sites if you're interested in that publication. What is interesting about the US network that was funded by the NSF is that my dear colleagues have chosen sites where there is no human influence. It was a little bit interesting to see that in the United States, scientists they still think that they can find places where humans didn't play any role in the history. Incredible. This is related to the wilderness concept, which is really present in the American culture. In Europe, there's no way you can do that because there's no square meter that hasn't been cultivated or managed over the long time. So what we did in France is a different approach. As I said, we have a long tradition of observation in France. The problem being that these different observation sites have been developed by different disciplines. So you have an hydrological site, you have a geological or biogeochemical site, you have a site which is working on erosion, blah, blah, blah. But usually these sites were not communicating, were not talking to each other, blah, blah, blah. So we created a network which is called OSCAR, Observatoire de la Zone Critique, Application et Recherche, Critical Zone Observatory, Application and Research. You can see, you can have information if you want on the web page. I'm not going to go into the details here, but it is a network which is putting together observatories led by different disciplinary fields. Okay, so cryosphere, the watershed observatories, we have observatories for peatlands and swamp areas. We have observatories for the deep aquifers in the critical zone. Okay, so I'm not going to the detail. This is the sites that are monitored within the network. We have sites in the south because the French teams have a long tradition of collaboration with countries from the south, South America, Central Africa, and Southeast Asia. And there are a number, if you're interested by the type of sites which are studied, you can go on the webpage and there is a detailed information for each of these sites. Okay, just give me one example. This Strengbach Critical Zone Observatory in the Vosges was created back in the 90s and 1990s. And the 90s, you were not born, but I was born, and the main environmental issue was not climate change. It was acid rain. All the forests, like this one here, were dying because the rain was acidic. And we knew already at that time why rain was acidic. It was acidic because of the sulfuric acid, which was rejected to the atmosphere, released to the atmosphere, in particular by the industry in Europe. The problem has disappeared, in particular because we have cleaned up the coal that we're burning, but also because we got rid of our industry. The industry is now in China, and in China is one of the regions of the world where the problem of acid rain is still a big issue. Okay, and so the Strengbach catchment is an observatory. It still exists, and 40 years or 50 years later, we have a long-term chronicles of data showing how the ecosystem is recovering to this extreme event, so to say. That was the acid rain forcing back to the 90s. And this is, for example, a record of the sulfate ion in the stream. So let me just explain why we're monitoring sulfate. Sulfate is an ion. It's something that you measure quite easily in your lab. It's a dissolved molecule in the water, and it's a good indicator of how much sulfuric acid is coming from the atmosphere. Okay, so basically, if you do see sulfate, if you see sulfate decreasing, which is what you do observe here, back to the 90s up to now, you do see a decrease in the river. Okay, of the sulfate, it tells you that the amount of sulfate of acid, sulfuric acid, which is causing the acidity of the rain, has been decreasing. But what is interesting is that, okay, you observe a long trend decrease, but you have like peaks and valleys that we basically don't understand, meaning that there is something happening in the ecosystem which is related to the input of sulfate by the atmosphere, which is doing something that we still don't understand. And you do see something interesting, which is here. The sulfate concentration of that stream, particular stream here in the eastern part of France, is not decreasing anymore, and it's stagnant. And we know that because we've been studying that quite heavily. We know that this is acid rain or sulfuric acid from China, which is coming back through the general circulation. So it's interesting, like it's a boomerang effect, okay? We got rid of an industry in Europe, so we think we got rid of the acid rain problem, but the acid rain problem is still there because the industry in China is changing quite a lot, but the industry in China is still burning dirty coal full of sulfur, but it's reintroducing acidity in Europe because everything is connected on that planet, okay? This is not because the Strangbar Basin has its own local peculiarity that it's isolated from the atmosphere. Okay, and look at, it's interesting, I like to show that to my founders. If I just study the system during 3 years, there's nothing I can say. Okay, I really need 50 years of study to know something about my system. Okay, 3 years is the duration of a PhD. Okay, so you can have like many PhDs if they are continuously funded if you want to know something about the system. Okay, so this is to demonstrate the virtue of having a long-term monitoring. And if you're interested, there is a movie that we have made on that particular observatory. Okay, so what does it change? I'm going to end up in a minute. Huh? What does it change to the Earth politic in the Anthropocene? It changes a lot because this critical zone is a zone which is the habitable zone of the planet. Okay, there, as I said already, we're not living on the globe. We're living on this very, very thin pellicule, and by critical we also mean that this is a pellicule we need to care of. Okay, the first time I met Bruno Latour, a philosopher, he gave me a phone call and I said, "Oh, hello, I'm a philosopher. I'm interested by the term critical. Why did you name that critical?" And I said, well, I said before, oh yeah, it's a National Research Council in the US. This is a critical zone of the planet because it's causing blah, 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 blah. And he said, yeah, but you know that critical is also something which is really important for the social sciences, because by critical you mean that this is really what you need to care, to take care of, and so it opened a new avenue of research. This is, yes, of course, this is a critical zone of the planet because this is a zone we're living and this is a zone we're destroying. And in some cases, we're destroying it at a much faster rate that it's being created. Okay, these processes that I've described earlier, are slow by nature. Okay, and so the problem of humans basically is that they trying to coexist with a system which is too slow for the velocity at which they want to use it. Okay, and so we have a big issue of desynchronization. We are, from a geological point of view, we are a species which is disconnected from the temporalities of the system. Okay, this is my definition of the Anthropocene. And so I like this figure. It's another ugly figure. I will end up by showing you a good figure. Okay, so this is the system, the critical zone system, the atmosphere, the biota, the soil, the sediment, the aquifer, the lithosphere, everything more or less, you know, in equilibrium before this small guy present in an infinite amount of mass at the surface of the planet is completely disequilibrating the system by destroying the soil, by injecting into the soil molecules which are toxic molecules, which are basically killing life, and by, of course, putting concrete at the surface, so preventing the water to infiltrate, and so suppressing the water cycle. We are really a strange species. And so, yeah, the consequences are terrible, but I'm going fast on that. Yeah, this nice picture is an observatory, a critical zone observatory from the OSCAR network. You see these horrible things here. This is places where erosion is extremely high. This is places that during the last century were covered by grasslands, but they have been overgrazed because the people living there were too numerous, and then they cultivated too much the soil destroyed at some point. This is a Mediterranean climate, so as you know, a single storm can destroy the soil for 1,000 years. And the soil, and this is a place where experiments are conducted to understand the velocity at which a soil which has been completely destroyed here, which is completely eroded, can be rejuvenated. Okay, and so this is an interesting observatory. You might be able to visit these observatories if you're interested, and you can contact the PIs. Okay, I'm passing on that. And so, why is this critical zone important for a new politics, okay? So the critical zone is an hybrid object. It's both a social and a natural science. It can be studied by both social and natural sciences because man is one of the agents, okay? Humans are participating to the transformation in the Anthropocene of the critical zone. So the critical zone is different from saying, okay, we have humans on one side and we have the biophysico-chemical template on the other side. And we're trying to look at the relationship between humans and nature, okay? If you notice, today I didn't pronounce the name nature, okay? This is not a term I need, and this is not a term I like, by the way, because I think this is a very misleading term, okay? It's a system, and we are part of the system, okay? And we have been desynchronized from the system, and our point is now to be more respectful of the temporalities of the system. So it's a new way of looking at the ecological crisis. It calls for an alliance of all natural sciences, bridge ecology and geology, which is not nothing, to sociology, anthropology, arts, politics. So I'm working with anthropologists. We are interested by an anthropology of the critical zone, which is something which is really important to do, okay? And for example, when you look at Philippe Descolat's work on the tribes in the Amazonian plain, you know that they have a very different representation of the world, which is not nature and humans, nature on one side and humans on the other side. They have integrated the fact that they are part of a system, okay? And so the anthropologists from who I'm trying to work are anthropologists which have studied this ontology of the Pachamama in the Indian culture, which is very close to the critical zone concept, actually. So this is interesting that former native cultures are, the way to put it is that scientists are rediscovering, so to say, representation of the world that have been made a long time ago by native cultures. Okay, and so what is important also to renew the way we can do Earth politics is that the critical zone science is place-based, okay, as I showed you. There's no point of doing a global critical zone science. Nonsense. So the critical zone is place-based, and we need to understand the local, okay? We need to compose the globe in terms of local features. Of course, we need to upscale at some point, and political decisions need to be upscaled, of course, but it's starting from the local, okay? And this is something which is completely different. This is the places to land, to redefine the best politics for living within the system and not on the system, okay? And we need to change our representation. I kept my time saying that, and so now I'm going to show you what we're trying to do. So this is work we've been conducting with an architect, which is Alexandra Arène, and Bruno Latour. So you, on the top here, you have the conventional view, okay? The Earth's core, the Earth's mantle, the Earth's crust, blah, blah, blah. And the habitable part of the planet on that conventional representation is not even visible. It's not within, oops, it's even not within the outer, trait. This is ridiculous. We have representation. We don't have representation of the planet we live on. Yes. And it's coming back to Galileo that told us that the planet was one of the planets of the solar system. Okay? So Alexandra has this very brilliant idea to say, okay, we're going to invert everything. And this is a new representation. It's here. So we, what was at the outside, the atmosphere, infinite, is now in the center. It's here. It is a white part of the diagram. And then when I go, when I go to the outside, outer part of this new globe, I'm going deeper, and I'm going to look at a longer time scale. Okay, so the first layer would be the topsoil, the arable soil, okay, or the vegetation, which is taking up CO2 from the atmosphere, for example. But then I got the geological soil, my saprolite, which is important for the water resource also, so I'm really depending on that. Then the crust, I'm depending upon the rocks which are present in the continental crust, because this is a source of the nutrients. I'm not depending that much of the mantle, and I'm not depending at all of the Earth center. Okay, so what was in the center of the representation is now completely, peripheral. Okay, and this is what is interesting about this representation. And so we published that in 2018, and we've been working on that representation. With an interesting, I don't have the slide here, an interesting program which is called Terraforma, which is the name, by the way, of a book which was published by Alexandra and Frédéric Atouati, which is an historian of science, which is to invent new representation of the world. And eventually, these new representation of the world are based on data which are collected by the people that live there. Okay, so we have a big program which is called Terraforma, based on the name of that book, which is to develop low-cost sensors. So it's really a technical program, but to give these sensors to people living at a given place. And I met a lot of people that are really interested by having these sensors and participating to the data collection. Okay, so in that conception, the data are not acquired by some scientists that come once every 2 weeks on the field and go back to their lab and and do publication with this data, but they are really, an interface between the society. And this is one of the way we can make people aware of the transformation and ecological crisis we are experiencing. So this is really a new way of working on the relationship between science and the needs of the society in a transformative way. Okay, and so it's working itself. Okay, so what I wanted to conclude was that there is a big hope. I'm going directly to this. Yeah, if you're interested, you can look at Bruno Latour's book at the end of his career. They've been translated into many languages. Were really focused on that notion of critical zone, not in that my sense, I mean the scientific sense, but in the sense that basically we are confined in the critical zone. Okay, we're not leaving the planet. We are hanging in mid-air, like the citation was saying, meaning that globalization is not our future. We need to land, and we need to land on places where we need to get a lot of information, okay? Because the habitability of those places is really the challenge. Okay, and so you can read this book in particular, Où suis-je, or the other one, où atterrir, which have been translated by many other words. And there's really where Bruno, which is a philosopher, is trying to develop this interesting concept. Yeah, où atterrir, down to earth in English, which is a pretty good. Okay, and this is, and I will give you this slide. You will find here a couple of references. You can have nice interventions here of Bruno and also Frédéric Attuati, which we are working. Just to conclude, I'm not going to read this conclusion slide, but I've spent most of my week on a big program which is called Transform, which is associating ecologists, geologists, social scientists, artists, and citizens on a program which is going to, we hope, last for the next 10 years, in which we want to create what we call Earth Habitability Labs, which is places where we want to do these experiments that we really now need to work on a particular question. It can be a question around water, it can be a question around the soil, it can be a question about biodiversity, but putting all these people together. I think one of the problems we have right now in the ecological crisis is that it's very difficult to make all these people talking to each other. And again, the way scientists, experimental scientists have constructed this critical zone initiative is, I think, very informative, inspiring to go to make something broader, okay? And at the local site, this is a key, at the local site to associate different communities working on the same question. It's complicated because our funding agencies are not designed to do that. Okay, our funding agencies, they find it very easy to give money to a single researcher to hire like a PhD or postdoc position, but it's very difficult to found, for example, a farmer with which you want to work, because when he works with you, he's not on his field and he's not producing his own salary. He's not making his own money. So you have to find a mechanism, a funding mechanism, which will encourage the people living on a given territory to work with the scientists. So this is a challenge, and I'm pretty optimistic, and I think that's going to make it. And I thank you, and we can take some questions.
Thank you. First, I have a remark, is that I understand your point of view to gather all this field of science, but what I think is that we know already a lot of things that are bad practice or good practice, and I think that you present your work as if there was it as a hope for to change things, to have a political impact. But to me, you know, the problem, for instance, of agriculture practice, we know a lot of things to make it better, and it doesn't get better. Most of the time, I mean, sometimes yes, but not as a whole. So first, I wonder what would be the impact, because I can see it now. How could there be an impact? And I have another question, because from a scientific point of view, I mean, those questions I think are really very interesting. That how men of our humanity, or whatever you call it, can project itself in the long term. Because for me it seems that the history of mankind is somewhere always putting away this question. And no, you put this question on the table, which I think is a very important question if humanity, if human as a species, want to remain there in the long term. It has to manage with these questions. And you mentioned the person which is at the origin, your hero of geology, who really have this question, and I asked myself this question too, but you take minerals from the ground, you heat, and you deplete the ground. And I think there's this question of how long it can last, because agriculture, you think, we still produce food for decades, and it can last. You can think that, well, it works. It works. It's okay, you know. But, well, how long will we be okay? And also the problem of erosion, the problem of organic matters in the soil. I think that those questions, it seems that we always delay because it seems that it's not that urgent. And I think it seems to me that this very important political questions is always postponed. And this is a major problem, I think. So what do you think about all the things I've said? Thank you.
Hello, my name is Matilda. If that's okay. Sorry, that's how we often do it. I have a slightly technical question where I just didn't quite understand when you were talking about the Amazon, and in particular how flat surfaces are less robust because of the sort of conveyor belt analogy of the critical zone not operating. If you could just expand on that to a non-scientific audience.
Hi, Lucien. I had a question with regarding the anthropologists that you work with, specifically with the citizen science that you mentioned with Terraformer, and I'm guessing this Earth habitability labs as well, because so you said you were working with anthropologists, but more so on the sort of representation of the critical zone and the ontologies, etc. But I know that there is a lot of anthropology on citizen science, especially to do with the environment, etc. So just wondering if that was also an area where anthropologists and geologists, etc., combined.
Okay. Yeah, there's a lot of things. Just to start with the technical question, so the Amazon, when I say that the Amazon is dead, the idea, if you look, I mean, the Amazon is, you have the forest, and then you have probably like 100 meters of material which is not rock, which is decomposed rock, which is soft, blah, 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 exactly my critical zone. So that a tree, even a tree with very, very deep roots cannot access to this source of nutrients, which are the rock, okay? It's too far. It's too far. And the reason that with time, these reactions of transformation of rocks into something else have continuously have occurred with no compensation mechanism at the surface because erosion is too slow. So we are in a situation where you accumulate the waste, so to say. You don't remove the waste of the reaction, okay? And so at the end, you kill yourself, you know? It's impossible for the roots of the trees to get the nutrients. It's impossible for the roots to access to the water, which is too deep, etc. So the only way the Amazonian forest can survive, can be sustainable, is to recycle everything. Every single atom of potassium is being recycled, which is not working perfectly because nothing is working perfectly in nature. In the Earth system. And so there are recent studies that demonstrated that the fertility, the long-term fertility of the Amazonian forest is the Saharan dust, which is crossing the Atlantic and is deposited on the Amazonian forest. It's very low amounts, but it's enough to sustain the forest over geological time. You have to know that the Amazonian forest has been stable for probably 200 million years. It's incredible, okay? In Europe, for example, we don't have such places because Europe is a mountainous region, basically, okay? This is a collision between Africa and Europe, and that's great, all this relief. So Europe, by comparison, is a very active region. My conveyor belt is much faster than the slow conveyor belt in the Amazon. Did I answer? Yeah. And the more serious stuff. Yeah, so what you said, we know, basically you said we know everything. There is an urgency and we know everything. I don't agree with that. There are plenty of things we don't understand. But where you're right is that science is slow and markets are very rapid. Very rapid. Markets are working within a second, as you know, okay? So when something is making money, poof, it's going very fast. Let me give you an example. So these weathering reactions I've talked earlier, okay, this CO2, blah, 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 are being used by some people which are creating companies, startups. Right now, in the US, for example, there is a market. We don't understand the process. We don't know what are the fungi, the bacteria which are doing things, but some people have already decided that they are going to crunch rocks like this, put it over like agricultural fields, that it will consume the CO2. We, the scientists, we can do nothing. Nothing. We can say, oh, be careful, we don't know what is going to happen, you know, you playing with the fire. But it's too late. I mean, the market has decided, and there are billions in the US, and in particular in Stanford University, is paying for, you know, chairs of people, colleagues, working on what they call enhanced chemical weathering. And that's it. And so as a scientist, I have no choice. I mean, I need to continue my research, even though I think that I'm not going to, you know, to control the system. This is really a market thing. And so tomorrow, for example, let's take one other example, biochar. Have you heard about biochar? So biochar has been presented as if it was the solution. And now, like, and there is a big market with biochar already. Huh? And now scientists, and I spent 1 week last year in Vienna at the annual meeting following sessions on biochar. Actually, we don't know what is going to do biochar in, I mean, the stability, so to say, stability of biochar is being questioned every day now, because we don't know the long-term stability of the biochar. Okay, so it's not that stable actually. So, you know, science is working like this. Scientists are proposing some things, then the markets, some people are creating markets around these discoveries, but the discovery, and this is the way science is working, can be, you know, new after 10 years, but the market is not going to change because there is a market. So I have no solution to these problems, but when you say, okay, we know a lot, and basically we know enough, no, I don't think we know enough. We still need active research on all these problems because I don't think we understand the Earth system well enough. But again, this market thing, I'm completely, I can do nothing. As a scientist, I can do nothing. But this is not a reason for me to stop working. And second question was, I really think we need new narratives. I really believe in narratives. And we're not going to save us with the present, with the narratives we have now. Okay? This, in particular, one of the narratives, and I mean in the Western culture, the fact that there are humans and their nature, and humans is doing bad things to nature and blah, 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 it doesn't work. We're not going to continue that way, because if we want to coexist with the system, we need new narratives. And maybe I didn't insist on that, but what I'm doing when I'm trying to work on that critical zone concept, I like it because it's a new narrative. And it's a narrative which is, and this is your point, by the way, which is taking into account the different temporalities. Because I think one of the problems we have by making our policymakers aware that there is an urgency is that we are not telling the story with all these time scales, embedded. And the Earth system is characterized by plenty of time scales. And there's no way you can only consider the smallest time scales, okay? The long time scales are important as well, okay? And typically the biochar thing, the biochar is what geology does in hundreds of millions years, but with the biochar we're trying to accelerate it. We're trying to resynchronize to the geological cycles. And I think there is a lot to be done for us, our species, as you said, to make efforts to resynchronize to the system. And maybe some geoengineering is in order, okay? I'm not rejecting geoengineering, but I think there is good and bad geoengineering. And the bad geoengineering being that when you don't understand fully a process, be careful of not applying it too widely, because you don't know what are going to be the consequences after a while. After the first and short time scale have been done. And then there was another question on anthropology. Yes, so I don't remember exactly what was the question, but.
On whether you work with anthropologists on citizen science rather than just on the anthropology.
Yeah, so there are several initiatives which are starting. But the anthropologists I'm working with are trying to, in South America, you know the problem in South America, the state is trying to impose some rules which are not consistent with the local rules, which are the rules of the native people, which have a different ontology. And so what is interesting with this critical zone concept, because it's kind of, coming back to this ontology, is that it's a hope, so to say, that even the decision from a state can be consistent, compatible with what the people have in mind as a representation of their habitable world, so to say. But it's just the beginning. But just to give you a very concrete example, you have now earth science laboratories in which anthropologists are being recruited to work with the geologists. And there is a huge literature on the geological anthropology. In anthropology, which is taking the long time scale into account. Because when you go into, when you look at the Pachamama things, the rocks are respiring in the Pachamama, culture. And so what I'm trying to explain today is something which is evident for an Indian. Yeah? So it's really interesting to. Okay. Did I answer to everything? Probably not, but no, he's not satisfied.
It's just that I think there is a misunderstanding about my first point. I just said that in agriculture there are a lot of practice that are wrong, and we know it. And I didn't say that we know everything about what you mentioned about biochar, whatever. But I say that we know that there are bad practice and better practice in. For instance, we have Gilles Billen. There was Gilles Billen there a few weeks ago, and he's kind of promoting another kind of scenario that which be much better based on the nitrogen cycle. So that was my first point. That's what I want to say.
I was just really curious, due to your collaboration with Latour and apprehension of using the word nature. I was wondering if you share his more anti-essentialist stance, and haven't had the chance of, maybe as a geologist, what this, like, if there's a debate going on as well among geologists about an objective nature, and what repercussions you feel this would have on the topic of sustainability.
A debate within the geological community
Academic field of
and the relation with Bruno Latour, what is it?
with kind of rejecting that there's a nature beyond society, and
The problem with geologists, okay, what is a geologist? First question. And actually, this is not a tricky, this is a tricky question. I don't think, well, geologists, you see, I mean, we have, I mean, we talk a lot of the earth, but you never see any geologist, you know, in the media. They're just absent. And then we're talking, every day we're talking about the planet, the earth, okay? But this is not the planet, they're not living on the same planet, the geologists, okay? I told you I'm a geologist, but I'm a, how to say, heterodox geologist, you see the analogy with economy. The people like me are very rare, you know, and the narrative I am trying to give you today is trying to say to my dear colleagues, oh, something is happening. Okay, humans have become a geological force. We are into the Anthropocene. Maybe you followed this dispute on the Anthropocene. It was quite interesting that the geologists last year rejected the term. You know that, huh? They didn't vote it, because they think, no, it's nothing, you know. The Earth has experienced so many big things that it's a really small thing. They're completely stupid, of course. And I wrote a paper in Le Monde to say that, you know. They are stupid. They're missing a unique opportunity for their science to, you know, to be the important science in the Anthropocene. So their fault, and they're going to disappear. And that's good. But the geologists, the problem of the geologists is that they have been extractivists for decades. I mean, most of my colleagues in the geology field, they were having a lot of money just like in half an hour or 10 minutes by talking to Total, Shell and other oil companies, because these companies were extremely rich and they were wanting to find new gas reservoir, blah, blah, blah. So it was very easy for the geology, mainstream geology, to get funded. No problem. Huh? Time has changed, and now you will find a lot of geologists which are just crying that they're poor, that they cannot conduct their research, blah, blah, blah. They didn't understand that the science must change, and they have good tools. They have a good way of thinking, and particularly they are working with all these temporalities, and they can address the problem that humanity is facing in a very original and new way. So this is my, how to say, crusade to try to convince my dear colleagues. I don't think I'm going to be extremely successful, but you know, it was trying. And so for these geologists, yes, they're not working on nature. No, it's not. It's absolutely not what they're doing. I don't know if I answered.
Why would you say you would abstain from saying nature and instead describe it?
Because nature refers to this Western culture that's coming from the 19th century, that nature is some kind of landscape on which we are posed, and that we try not to disturb too much, but it's not the way it is. I mean, for example, I really don't understand this notion of integral natural reserve. I think it's completely stupid. There is no single place on the planet which is not influenced by global warming, the amount of CO2 in the atmosphere. So the tree productivity has been changed just because by the fact that we have put CO2 in the atmosphere. The ocean is being acidified by the atmospheric CO2, blah, blah, blah. So this idea that I'm going to create places where it's forbidden to go, it's ridiculous, really ridiculous. And I do think we need to change that. And when you see that Trump is being elected in particular because he says there's too much rule, there's too much ecological rule, this ecology is a punitive ecology. I mean, this is exactly the reaction that the bad reaction which is due to this kind of narrative, I think. Okay? Go to a farmer and tell him that no, he can't cultivate here because it's a natural reserve and he can do anything. He's going to laugh at you. He's going to tell you, who are you to tell me what to do? You know. And so I think this is a real problem we are going to face. Ecology is not going to unify everyone. Ecology is going to go. We're going to go to have wars with ecology. I'm not kidding. I'm sure. And this is one of the reasons I think we need to change our narrative. And I think the narrative of culture, nature, and culture is terrible. I remember during the lockdown, Dominique Jadot is one of the French leader of the Ecologist Party, was saying at the radio each morning, the government needs to open the Bois de Vincennes. This is one of the big parks in Paris area, because the Parisians want nature. They want to access to nature, like if the Bois de Vincennes was nature, you know. And so, what is nature, you know? So, you know, this kind of narrative is going nowhere. And look, the ecologists, they do what? 3%? They're talking about the most important problem the humanity ever faced, and they're doing 3%. There is an issue, a big issue, really. So again, I really think we need to change our narratives. And it's not a detail. With these good words. Other questions? No?
What kind of politics?
Politics?
Yeah, what kind of politics?
Science.
Science? Yeah, so science-based politics is what?
And politic-based science.
Politic-based science. Yeah, and also science-based.
Yes. Yes. We cannot continue the way we did for centuries, that's for sure. There's a lot of work.
I don't know if you are the center of the movement, but is this movement international or is it really?
I don't know what movement you're talking of, but I'm contributing at the place I am.
These ideas, I mean, is there?
My feeling is that things are changing, yes. Yeah. But things are not going to change because we decided that we are bad humans on a pure, you know, ideal nature. I don't think so. You can hate me, don't mind. Okay. We end up?